well, time's up, so I'm just gonna start. So hi everyone, my name is Raphael. I work with Biksha, and traditionally the GANs lectures are done by a student of Biksha, who usually is Ben Striner, but he's not available today, so I'm doing it in his place. He made the most of the slides that you're gonna see. And he's very skilled in regarding GANs and things like that, so you should find it satisfying. So generative adversarial networks, you've probably heard of them. Definitely heard at least the name if you don't have at least a rough idea of what it is. So they are very powerful models that are, for example, at the core of deepfakes model that you've definitely heard of. And they can do a lot of cool stuff like that. So we're going to talk about them in a set of 2 lectures, today and Wednesday. So today we're going to go over a bit of general content about GANs and what they're used for and the motivation behind them. We're going to put them in the more general framework of generative models in machine learning. We're going to see a bit the theory around GANs. We're going to see how to evaluate GANs, which can be a little tricky. And we're also going to compare GANs and VAEs that I think you haven't studied yet, but you will next week normally, if I'm not mistaken. And we're going to go over a bunch of architectures revolving around GANs that can do some specific stuff or that improve on the original GAN a little bit. All of those might be useful for most of your course projects, I think, so that's at least one good reason to pay attention. So what are GANs? Generally speaking, they are a tool for generative modeling. So we're going to see what a GAN is, how do they work, what you can do with them, and also how to, in practice, make them work and come through a bunch of optimization problems that they raise, but that final point will mostly be the topic of next Wednesday's lecture. So I told you GANs are generative models, so that means that they are used to generate samples from a distribution. So that should be a little different from most of the things you've studied so far. For example, you give a GAN a data set with faces, the GAN is going to learn to generate new faces that look realistic. You give it music, it's going to learn to generate music. You can give it music from a specific musician that you like, and it's going to learn to mimic the specific style of this musician. So that's the kind of very cool things that we can do. It works with pretty much every modality, from image to video to audio to text. Today we're mostly going to focus around images because it's easier to display on a PDF. And we're going to start by seeing some of the cool stuff that have been done recently and less recently with GANs. So that's the original GAN paper, where the original architecture was used to generate images that look like they're from the MNIST dataset, for example, on the top left, and also the faces in like some examples from the CIFAR dataset too. You can see that I think it's like at the time it was just pretty impressive. Today you could argue that the faces, for example, look a little blurry, and even though it's pretty impressive to be able to manage that, it's not exactly photorealistic. But if you look at the improvement over the years, on the right, you can see what can be done now. So remember that the woman on the photo does not exist. She's been completely generated, but I don't think you can guess that by just watching the photo. So that's how good the models are after 5 years of progress now. So you can train GANs. A lot of the improvements have been around training GANs on bigger images, bigger data sets with more features, and to train them faster on a bunch of, if you want to generate a lot of images. So it used to be 28, 28 or 32 times 32 images. Now we can do 512 pretty easily. But what you need to remember is that it's not only generating faces, it's also, or generating data, it's also understanding this data much better. So by understanding, we can mean a bunch of different stuff, but for example, if you give the GAN the faces with different sentiments, like or like characteristics, like some are blonde, some are male, some are female, some are old, some are young. And some GAN architectures, if you supervise them correctly, they can isolate those features and transfer them on different images. So for example, if you give an input face, you can make that person blonde, or you can make them older. You can change the gender, change the emotion. You can do all those kinds of things. So that means that, at least in one way, you've understood what anger, for example, or age is in the data manifold, and you're able to use that to your advantage. So that's the kind of things GAN are able to do. Kind of similarly, you can use them for example, style transfer. You can take images from day, you can turn them to night. You can take sunny weather, turn it into a snowy or rainy weather, etc. I'm not going to play that video, but I'm going to play another one. So another thing, a cool thing you can do in the area of understanding, hold on, GANs. So that's a model that's trained on faces. And look at the things you can do. Now what this means is the model is able to interpolate between faces. That means if you take two different generated faces and you just on the input space you draw a line between the two, most of the points on those lines are not going to be faces anymore. There's going to be some blurry thing in the middle. But with GANs, you can actually draw a line on the manifold, how it's called, of faces, and interpolate between two faces where all of the intermediate points are realistic faces. So that's pretty cool. There's a lot of things like that you can do. You probably found, you probably saw some in the media before today. In GANs, the G stands for generative. That actually goes a long way back. Generative models differ from discriminative models that should be most of the ones that you've seen so far. So in the discriminative models, you've got, if you've given, say, inputs X and labels Y, that could be figures for MNIST, or if you're doing speech to text, like you've probably done, Y would be the phonemes or the sequences of letters. Then you're learning in the discriminative network, you're learning the probability of the output Y with respect to the input X. In a generative model, you're just learning the overall distribution of the data. So if you got X and Y, it would be the joint probability of P of X, Y. Why would you want to do that? Well, generally speaking, the joint probability is more general than the conditional probability of Y given X. So for example, from the joint probability, you can find back the discriminative version using the Bayes rule, but you can also do the opposite, find the probability of X given Y. And generally speaking, you understand a lot better what the data is. Plus, in this framework, you don't actually need a Y because you're just learning the distribution of whatever is given to you. So if you just have one data format X, you can also do a lot of things. So with that way, you can leverage unlabeled data. Have you seen autoencoders? Yeah. Well, autoencoders are not generative, but they can kind of do that too. You use unlabeled data, and you learn to reconstruct it from itself. So generally speaking, generative models are, you could say in that aspect, better than discriminative models, but they come with a big drawback, which is that they're much, much harder to learn than discriminative models. I think you can get the rough idea of why just by thinking about it, because Y is usually, as opposed to X, pretty easy, like the labels as opposed to the image. Like the space of the output Y is an easy space, so you're going from the complex to the simple, which is more, which is easier than going from the trying to generate something that's complicated like X. It's just in terms of dimension, generating something of dimension 1 or a few numbers is much easier than generating something of the dimensionality of X, which is in the millions sometimes. So that would be the general viewpoint used to be that if you're given a discriminative problem, you should solve that problem directly, not try to solve a more general problem and then downstream to the simple task. So that's something that Lapnik said a couple of decades ago. Very important person in machine learning. This is the same that in VC dimension. He's the guy that invented SVM, etc. But you do have an alternate viewpoint. That would be that generative models may have a bigger error than discriminative models, but they also tend to converge faster because they have a different kind of bias, and you can use that to your advantage. So that's just a debate that's been going on for a while with a lot of generative models that were there before neural networks were a thing or were popular. But if you, today from now on, we're going to focus on neural network-based generative models, which are either GANs or VAs. We'll have a word about VAs later. So you have any questions at this point? Yeah?
How do you say error for a generative model if you don't have the calc?
Well, I'm thinking that previously, that's actually, if you're just trying to generate, that's actually a very good question that we'll go about around in the evaluation section. But for that sentence specifically, they were thinking if you train a generative model, but then you use it downstream on a discriminative task. So then you can evaluate like the other models. But that's a good question in general. Anything else? Generative adversarial networks, again, they were introduced in 2014. And the way that they generate samples from a distribution P of X is to train not one network to generate things, but two networks that are called adversaries. And they're called adversaries because their objectives are conflicting. So we're going to spend some time going over that. There's going to be a bit of text in the next slides. So the generator is one of the networks. It's the one trying to generate data. So what it's going to do is produce P of the X, the data you want to generate, given Z, and Z being some kind of latent representation that you get to choose what it is. So for example, you're going to pick a distribution. Usually it's a Gaussian, but you can do whatever you want. You draw samples from Z. You pass them as input to the generator. And the generator is trying to map that onto a realistic image. Now, what's the idea behind that? Remember that the generator, what you want it to do is draw from the real distribution of the data. But you don't really have access to the distribution. You cannot draw from it easily. Otherwise, you'd be done with the problem. But what you're going to do instead is draw from a simple distribution, and the network is going to learn to map the simple distribution to the complex one. So it's kind of like you know that if you take the standard normal Gaussian and then you multiply it by 2, it's exactly the same thing as if you had drawn from the Gaussian with variance 4. So it's kind of something like that, but much, much more complicated. So by mapping a simple distribution to something else, you're drawing from a different distribution. And the objective of your generator is to learn how to have that output thing be the distribution you're trying to sample from. Interestingly, the Z, even though it's random in the training, in practice, assuming your generator is already trained, you can see it as the latent representation of the things you generate. So for example, if you remember the example with the faces that interpolated, the way that would be done in practice is pick the Z from the corresponding to the first face, pick the Z corresponding to the second face, draw just a line between the two, and look at the image of this line by the network. And that's what you're going to display, and that gives you a continuous interpolation between two faces. So you get the rough idea of what the generator is supposed to do, but that doesn't tell you how it's doing it. Because if you want to train something like that, it's really not straightforward to see how you're going to train it. Because it's not like you're trying to generate a specific image, right? You're just trying to generate an image that you want to be realistic. So you cannot pick an image from the real data set, compare what you generate with that, and say if it's far apart, it's not good, because if you were doing that, all you'd be trying to do is generate the elements from the training set, which is absolutely not what you want. You want to learn the distribution. So what you're trying to do is compare one distribution with another, and you don't have any traditional loss function to do that. So that's where the second network comes in, called the discriminator. So the discriminator is a classification network whose job is to distinguish between generated images and real images. So it's labels. You train it like a binary classification network, and its labels are 1 if the image is real, and 0 if the image is generated by your generator. We're going to say fake images for that. That's usually the term that we use. So the generator's job is to fool the discriminator into not being able to tell that the images are fake. And the discriminator job is to recognize the two and classify the fake images as fake and the real images as real. So that's why they're conflicting. You see that they're trying to do the exact opposite to each other. The generator is trying to generate something that's fake, and the discriminator trying to say, yeah, no, but it's fake. But from the perspective of the generator, all the discriminator is a loss function. So an adaptative loss function, because it evolves along with you training the generator. The discriminator after training is pretty much useless usually. You can its only job is to guide the training wheels, guide the generator up to where you want to go. But once you're there, it's only the generator that you care about. It's the only one you need to generate stuff. So a picture is better than 1,000 sentences. So if you look at the pipeline, the generator takes as input random noise, as we said, drawn from some distribution that you choose. It associates that with a fake image. And the discriminator, its input is either this fake image or an image from the training set. And the discriminator is trying to say, this is real, this is fake. So that's what the objective is going to look like. Usually define it as a min-max game between the generator and the discriminator. So that falls into game theory. If you don't know about it, it's fine. Why am I not in full screen anymore? Up. Oh, no. OK, there's no way to do that. Too bad. Right, so what the objective, the loss function if you want, it's gonna be the expectation over the real data of log d of x, the discriminator, plus the expectation over your latent distribution of log 1 minus d of the image you generated from that sample. So that's just basically the cross entropy for the discriminator that you should be familiar with. So that's objective. The discriminator is going to try to make it as big as possible with gradient ascent, and the generator is going to try to make it as low as possible with gradient descent. So pretty straightforward so far, but we're going to go through a little bit of math to see if it falls on its feet. So one thing you can wonder is, from this objective on the top, what would the optimal discriminator that you get look like? Given a specific generator, assuming your generator is somewhere, what is the discriminator going to try to reach? So if you just write that in integral form and do a bunch of derivations, you're going to get to the conclusion that what the discriminator should output is, for a given image x, the probability of that image under the real distribution divided by the probability of that image under the real distribution plus its probability under the fake distribution. So now if you plug that expression into the original objective, you're going to see that the objective that we were looking for was actually some sort of divergence between the real distribution and the fake distribution, plus minus a constant. That divergence is called the Jenson-Shannon divergence. It's based around KL, but slightly different so that it's symmetric. So generally speaking, the generator is trying to make that small, which exactly amounts to making the two distributions being close to each other. So that seems pretty consistent, I think. Just like I said, the optimal generator is the one where there is no difference between the real and the fake distribution. Any questions so far? The theory is kind of necessary, and I'm assuming it's going to be all what's talked about in your quiz questions, so it better be clear. So like we've said, no, actually, we haven't said it, but I'm going to say it. The optimal point we talked about is stationary points. That means if you're there, you're not going to move anymore. Because if the generated data matches the real data, what the discriminator is going to do, it cannot make the distinction. So necessarily, it's going to output just 0.5 for everything. And if it outputs 0.5 for everything, then it's a constant function. So its gradients are 0. So the generator is not going to move either. So if you're there, you're staying there, which is good. But that just because it's stationary doesn't mean it's stable. So you should have seen a little bit of that with when you saw gradient descent and the Hessian matrix that's supposed to have its eigenvalues positive. And you've seen a little bit of that in convex optimization, but these kinds of problems are much, much more problematic in the min-max game. A lot of things can happen. We're going to go into more details Wednesday, but in the meantime, you should still keep that in mind so that you're not, I don't know, blind by GANs today thinking, wow, they're amazing, they have 0 problems. That's kind of one of the problems. They're pretty hard to make converge because for a lot of reasons, if you're not at the stationary point, there is no particular reason that the gradient arrows are going to point toward that stationary point. So there's, I don't know, yeah. So if you look at this, on the top left, you can see what the gradient directions would look like on a standard GAN. The others are some different versions of GANs, but we'll go around that later. So you can see that in the middle, there is a standard point where all the gradients are 0, but all the arrows go over that point and not toward that point. So that involves, again, a lot of factors that we're not going to go over too much today. But it's the ugly part of GANs is that if you want to make those arrows go where you want, you're going to need a bunch of tricks about how much you train the discriminator as opposed to the generator, what are the different learning rates, a ton of different stuff, variations over GANs that are going to make everything work out. While by default, a lot of things could happen that don't work how you want. The takeaway of that being, if you're using a GAN for your course project, do it early so that you can try all of those tricks that we're going to talk about Wednesday. Another one of the ways one of the way this difficulty to optimize manifests is in the sensitivity of GANs to hyperparameters. So they are extremely sensitive. So we're going to see what happens if you've got, on MNIST, for example, if you've got correct hyperparameters. If it works. Oh. Well, you can do that at home. We're not going to spend too much time waiting that internet comes back. But the you'll see that the good hyperparameters lead to conversions that seems to do exactly what you want, where the images get better and better with time. But with bad hyperparameters, you can just like cycle around meaningless stuff and go absolutely nowhere, or go into median where you generate something super blurry. A lot of things can happen. All right, so the next couple of slides, they are both kind of a bit out of topic, but also in a way the most interesting things we're going to talk about today. But we're going to stay high levels on that. So that's about perceptual distance. So you know that when you train, for example, images to be like this or like that, you use a loss like the L2 loss, supposed to say if the images are different, this thing is going to be big, and I'm going to try to make it small, and it's going to get me wherever I want. But those losses are always surrogates, as you've seen, and usually they're not perfect. You can have two images that look very similar to the eye, but from the perspective of the loss that you're looking at, they seem very different, and so your network is not optimizing exactly what you want. All the losses that we traditionally use with our models, they are not representative of what similarity means instinctively. And from a certain viewpoint, that's the problem that the discriminator is trying to address. Because the discriminator is learning what similar means from the pure perspective of the data distribution, which is sort of the most objective things you can think of if you want to represent your data. So we're going to see a little later how GANs manage to do clustering and some amazing things like that. And that's because the discriminator is sort of addressing at the same time all the problems that your loss functions usually, or your minimization objective usually are. I don't know how clear that is, but for example, you can let's think about something. If you want your loss to have a certain property, like for example being shift invariant, you can just make your loss a CNN, and this loss, the discriminator is going to be a CNN, so it's going to get all the nice properties that CNNs have, among which being shift invariant. So you can sort of plug into your loss function whatever you want to plug, kind of. So discriminators are very, very interesting from that perspective, and you can see that as the reasons why GANs are so useful. Another thing you very much have to keep in mind, this time from the negative perspective, is that we said that generative models are learning to a distribution. But all they are actually doing is sample from the distribution, right? Like we've said, given you can draw from that distribution, generate some x. That's not going to give you p of x. So that means that, for example, if you were trying to do the things that we talked about in the beginning, like get back the conditional distributions based on the joint distribution, it's not completely straightforward. There's a lot of things that that generative models are supposed to do that GANs cannot do natively. But we're going to see a bunch of variations of GANs that are more powerful. But remember that, again, you're not able to assign a probability to an actual image. All you're able to do is generate images. Another thing you don't have is the encoder that could associate an image to its latent representation. So remember that I said the z, that's the input, is the latent representation of the image in the end. But the GAN actually starts with z, so you cannot go from x to z, which means GANs can not necessarily do everything you want natively. So that's another reason why we're going to see a bunch of architectures that tend to address that problem. That's also an advantage of VAs as opposed to GANs, like we are going to see very soon. So just to sum up, the good, the bad, and the ugly. The good is the results that GANs have. They can do some awesome things that look completely photorealistic in the case of images. The bad is the stability issues that they have, as well as the fact that, theoretically speaking, we've seen a little bit, but it's not that grounded. You may have thought, yeah, that's like when I explained the divergence and stuff, this is a little fuzzy. I'm not completely convinced. That's normal. No one is really convinced. But the fact is, it works. And so the ugly is everything you do to tackle those issues. So all the ad hoc tricks and small principles that people try to plug into their GANs to make them work. We're going on to evaluation. Do you have any questions on what we've just saw? No. So, evaluating GANs, it's not as easy. Like, I don't know if you think that's easy, but it is not. You're not, again, kind of like in the beginning, you're not trying to generate specific images, so you cannot look at the difference between the real and the fake to say, oh, my GAN was actually good. The only thing you can do is like look at those images. Are they are they realistic? How are you gonna actually evaluate that with, say, a test set? That's a pretty complicated and question where there are no very satisfying answers, but we're going to see the answers that actually exist. In a real generative model, the ones that take x and can give you the probability of x, the way you would do that is you pick your test set, you put it in the generator, you look at the probability that it has. If it's big, if real data is assigned very big probability, it means your model was good. So you could just, if you want to compare two GANs, you give them the same test set, you look at which ones assign the greatest probability to it, and that one is the best. That's how you evaluate language models, for example. Have you seen language models? Yeah, language model is when you use an RNN to generate text by from one word, you generate the next word, and you do that at every time step. It's basically just the standard RNN. And once it's trained to do that, the way you're going to evaluate it is pick some tests set, that's just a text. You put it as input of your of the model, and you look at the probability that the RNN outputs, and you just if you just play around and put an exponential and look at the loss per word, etc., you're going to get to a metric that's called the perplexity, and that's how you evaluate language models. So there are kind of different quote-unquote generative models, and that's how you evaluate them. But for GANs, again, you don't have the probability as an output, so you have no way to do that. So what are you going to do instead? Does anyone have ideas? Well, there's one at least that you probably thought of, even if you didn't raise your hand, which is human evaluation. So that's the one that in any good GAN papers you're going to have because it's the only one that seems to actually address all of the issues of the evaluation. So you take a bunch of people who did not participate in the experiment, like mechanical Turk or something like that. You have them look at images that you generate, and they claim, is this realistic? Is this real data? Is it not? And this way you output what they said in your paper. And if they say it's realistic, you win. The big problem of that, of course, is that it's extremely time and money consuming. So you can't really do that at every epoch to see how your GAN did on the validation set. You can only do it once in the end, usually. And also it's not reproducible. So you always have some, if you're trying to take a GAN, reproduce it, it gives different results. Yeah, well, that's because you ask different people. So there's no particular reason that they would do the same thing. So that's not completely satisfying from that point of view. But none of the methods we're going to see are satisfying. Another thing you can do, which is quite standard, is use another discriminative network to evaluate your GAN. So what that means is, for example, let's say your generated stuff, you train your GAN on ImageNet. So it's trying to generate ImageNet-like images. You'd expect, if your GAN is trained correctly, you'll expect the classes of those images to pretty much match the class representations in the original ImageNet dataset. So that means if you take the outputs of your GANs, you put them as input into a classification network trained on ImageNet, the labels should cover all of that you're going to get should cover all of the labels in the dataset. So by playing around that notion, that idea, you can get something called the inception metric, where you take the network architecture called inception, and you use it to evaluate your GAN by looking at the entropy of each of the different labels and saying all of those should be big. So that's called the inception score, and you see it around in a lot of GAN papers. That's what it means. If you want to know more of the details, you can look at the paper that introduced that metric. Note that it's a completely relative metric, because the value that you're going to get does not have any meaning in itself. What your GAN is going to give when you apply a discriminative network to it, it's kind of arbitrary. It depends on the discriminative networks. So what's important is that you use the same one that other people on the same data sets have used, so that you can compare. So that's why it's the inception score and not the AlexNet score. It's because we all have to use the same network so that it works. Why this one? I don't think there's a particular reason, except that that's what the first people to have the idea did. But use it. And finally, there is a final thing that you can think of, So remember how we said that you cannot, from a sample, compute its probability? Well, you kind of can anyway by cheating, so to speak. So if you have one image, you want to know what's its probability according to your distribution as the network, your generator modelizes this distribution. So what you're going to do is sample a billion or 10 billion images, and then you're going to look among those 10 billions, which ones are the image that I was looking at. And if it's like 15, for example, then that means that the probability of that image was 15 over 10 billion. Of course, you get a little problem if you try to do that, which is that it's a continuous distribution. So strictly speaking, the probability is 0, and you need the probability density and stuff like that. But you can work around that by, instead of looking at how many images are exactly the same, you take a ball around your images, and you look at how many images are in this ball, and you get back the probability from that. There's solid math behind that, but the problem is, of course, it's extremely costly because even on very small dimensionality problems, you need 100,000 examples. And for really big problems, when I said 10 billion, that was not an exaggeration. You actually need 10 billion images to get something that's meaningful. So that's a method that you would use most likely only on small dimension data. Because on large data, it kind of has the worst of both worlds. It's both a little fuzzy and not exactly giving what you want, and it's very costly. So problems of human evaluation and inception score. So that's pretty much it for evaluation. Yeah?
So why do you need that many images again?
Well, if you think about the images that are 512 by 512, because the dimensionality of the problem is so big, in high dimension, if you look at the probability distribution, and it's like kind of like a bunch of Gaussians that are around different points, all the center of those Gaussians have near zero mass, because that's just what happens if you have too many dimensions. So if you wanted to actually get a few images that are around that specific point, you're going to need to sample a ton until you get a few. And if you're under if you're just sampling 100 images, most likely you'll have 0 around that point, and you're going to say, yeah, the probability of that image was 0. But it wasn't. It's just that it was too small to be noticed. Any more questions? All right. So about VAEs, we're not going to go on too many details because you're going to see them later, but we're just going to do some high-level comparison. So VAEs, while GANs actually tackle the problem of minimizing the divergence between the distribution you generate and the original one, and because that's not really possible with traditional loss functions, we resort to using this min-max problem, and we've been over that. VAEs, what they're going to tell you is, I don't really need to minimize that problem, really. I can just I can compute this quantity, and this quantity is going to be a lower bound on the divergence that I was talking about. And if I just try to minimize that lower bound, it's going to do some, it's going to pretty much minimize the quantity too. So it's sort of using a surrogate of the distribution divergence problem and trying to minimize that. I'm not going to go over the math of VAEs because that's going to be later in the course. Just again, at a high level, they kind of work like autoencoders in the sense that you take an input, you associate it to a latent representation Z, then from that representation, you try to decode back the inputs, and if it looks like the original image, then you win. So it's pretty much like an autoencoder so far. The difference is, while in an autoencoder Z is completely unsupervised and it can look like anything you want, and most likely most of the points of the latent space are meaningless because the manifold is super complicated. In a VAE, you're going to add different training terms that are going to encourage this hidden representation to match prior. So the prior is going to be the equivalent of the Gaussian distribution that we talked about in the GAN. So you could use Gaussian, you can use uniform, you can use whatever you want. And then from that setting, you can compute a bunch of bounds on the divergence of the two distributions and say, I'm going to take this bound, I'm going to try to make it as small as possible, and hopefully it's going to have the same effect on the actual divergence. So in terms of pros and cons, because the VAs are not solving the actual problem you're trying to solve, but just an approximation of this problem, their generative process is a bit approximate too, and that's why GANs tend to have sharper and more precise results than VAs. On the other hand, VAs are much easier to make converge, and they train much faster, and they don't need as many optimization tricks. You can just put them, it's going to work. So if you've got, in practice, if you have a generation problem, most likely the smart thing to do is try with first the VAE, see how good the results are. If they're not good enough, then try again. VAEs, another thing is VAEs, while in GANs, the prior distribution, all you need to do is sample from it. In VAEs, it's going to affect your objective because there's going to be some sort of KL divergence between this distribution and the real data distribution, and you're going to need to compute the expression of that divergence. So if it's a uniform distribution, you'd have to change the loss function as opposed to if it's a Gaussian distribution. Another good thing about VAEs is that they do have an encoder, as opposed to GANs, where, like we've said, the latent distribution is just the input, but you cannot create it. The VAE has its encoder that goes to the latent distribution, and it's the encoder that goes from the latent to the data space. So you have the ability to go both ways. VAs are also a bit more theoretically justified, and it's very clear in the VAE to what extent it's going to work and to what extent it's not. And well, in GANs, it's more of a zoo of models where you pick whatever you can think of and you see what works. From an alternative viewpoint, the VAE generator, when you train it on the data that the encoder produced, but when you generate data, it's you just draw from the distribution, say the Gaussian, you put that in the decoder, and you see what outputs. So you're not looking at the same thing at inference time and at training time. And that's sort of an alternate viewpoint why VAs are limited in their capacity to generate stuff. It's because you're not doing the same thing at training and testing. Same thing we said before, but from a different angle. All right. No questions on that? Cool. So we can spend the next 30 minutes talking about some cool architectures over GANs. That's the list. Depending on how fast I go, I may have to skip one or two, but we'll see. So when you say GAN, there's sort of an ambiguity. It should be normally GAN means the vanilla GAN model, like the one we talked about, the one that just draws samples from P of X with the thing we mentioned. GAN can also, in practice, be used to refer to the entire family of models that we've talked about. Just like this course is called, like this lecture is called GANs, and we're going to talk about some different models now. All right, so here's the first variation. Conditional GANs. It's pretty straightforward. It means that you're not only trying to draw samples from P of x, but if x goes along with a label y, you're drawing samples conditioned on y. That means if, say, you're drawing from MNISTs and your labels are like numbers from 0 to 9, again, you're just going to draw samples that can be any of those numbers. But in the conditional GAN, you're going to say in the generation process, I want to generate a 0. And you're going to have to generate specifically zeros. Or I want to generate a 2 or 9, etc. So the way to get that is pretty straightforward. It's just that the generator is going to take as inputs not only the random z, but also the label. And the discriminator is also going to take the label so that it's able to say not only this image is realistic in the data set, but also it's realistic conditioned on that label. So yeah, again, if the picture helps you understand how this works, you just, there you go. You just concatenate the z and the y, and you get the x and the y, and that's the input that your networks are going to take. Here are the results that you get if you do that on the original condition again. So yeah, as you can see, you can choose the number that you're trying to generate. Sometimes you've got mismatches. Like on the row of 4s, a bunch of them kind of look like 8s. So that means like the process is not completely perfect, of course, and you can fail both because your image doesn't look like anything, or because it looks like an image from the other label. So. Next, so Lapguns or Laplacian GANs. Those are basically a chain of GANs that are going to solve problems that go from simple to complicated. So that's if you're trying to generate a very big image, like a 512, for example. The way you're going to do that is have, again, first train to generate these images, but in small dimensions. So you just get a new data set by blurring them and compressing them. You learn to generate those images. Then you've got a second GAN that is, this time is going to be a conditional GAN. And it's going to take as inputs both some noise and the image that the first GAN has produced. And it's going to try to generate a bigger and sharper image from that. Why is it useful? Because the original problem is extremely complicated, like we've said, and it has a ton of optimization issues. So if you try to solve a bunch of simpler problems instead, it might make things better. Because generating a face from a smaller face seems to be easier than just generating the big face. Strictly speaking, the intermediate GANs don't generate the image itself. They generate the difference between the big image and the small image that you just extended straightforwardly. So that's what the Laplacian part of the process covers. That refers to some processes that exist in image processing, where you pick the difference between the sharp image and the blurry image, and that gives you those edges that you can see on the slide. So you've got 4 GANs, like 1 GAN and 3 conditional GANs. That's how they did it originally. It goes from right to left, surprisingly. Any questions on Laplacian GANs? Right. I'm not going to go into the details of any of those because they're all different and there's a ton of versions anyway, so there's no point in going into the details of those specifically because we had to cherry pick the architecture we were going to put in the slides. But at the very least, you're going to have a rough idea of what they're doing, and if you need one of those, you probably have a good idea of which ones you should look at and what paper you need to read for that. Recurrent adversarial networks kind of relate to Lapguns that we just saw. Except that you don't train the different GANs specifically. It's just one very big GAN that takes its own intermediate outputs as inputs. So let's just look at the picture directly. So you see that you've got a first GAN generates something. That something is plugged as the input of the next GAN and it generates something else, and you've got a few time steps like that, and at the end you try to generate an image. The intermediate somethings, what are they supposed to be? Well, they're canvases in a way. So if you look at what the process gives with 3 time steps, see that you go from something, the shape of a number, to an actual sharp number, so that you've got the first intermediate thing on the top, and then the second, and then the final output. So this kind of mimics the process of someone that is drawing something, where you start by the rough canvas, and then you refine it until you get the final image. Again, they differ from Laplacian GANs because in Laplacian GANs you get different GANs that can be trained separately, and here you just got one big recurrent thing with just one backpropagation loop. Categorical GANs are doing clustering. So that might be a little, I briefly mentioned that in the beginning. It might be a little surprising to think that the generative model can be used to cluster the data. Know that cluster is like it's this unsupervised process where you look at an image with a bunch of points, and you're trying to say you've got 2 parts of this image. And let's just look at that example. So you see that you've got image that's drawn from 2 circles, and clustering this image means being able to divide this image in 2 parts, and say you've got the first set of points, that's the small circle, and the second set of points, that's the bigger circle. That's what you expect. But if you use traditional clustering methods like k-means, you're going to have something like what's on the left, where you just have a left part of your image and the right part of your image, or something like that. And that's because if you want to modelize the fact that your image is organized in circles and not in a bunch of blobs that are linearly separable on your image, you need some complicated modeling of what the data distribution is. And that's where the GAN comes in. Is there a next slide on that? No. So not going too much into the details of how the categorical GAN works. Roughly, what it does is, given the discriminator, if you give it an image, it's gonna try to not to say this is fake, this is real, but to say this image belongs to this cluster. And so it assigns, if you want there to be 2 clusters, it's gonna say this is in the cluster 1 or this is in cluster 2. And the discriminator is gonna try to be very certain of the labels of the real data and very uncertain of the labels of the fake data. So that's where the GAN min-max problem comes back. the generator is going to have to fool the discriminator, it's going to have to generate image that is very specifically in one of the clusters on top of just being roughly representative of the distribution. If you're not convinced, you can read the categorical GAN paper. Infogans are extremely interesting. They kind of address the problem of the lack of an encoder that we talked about, the fact that you cannot go from the image to its latent representation. In an infogan, you sort of can, but you're not going to do that for the entire latent representation. So the idea behind an infogan is, if I have say a figure from MNIST, what are how many features are there actually that are meaningful? That you can say the orientation is meaningful, the boldness is meaningful. There's a couple like that, maybe 10. But for you to have a good latent representation, you're actually going to have like 100 or 200 dimensional Z that you're going to need to generate something that's good. But in these 200 latent dimensions, maybe 10 are gonna might represent something that's useful. So what the infogan is gonna do is, say you've got two parts in the latent representation. There's C, which is what you care about, and Z, that's incompressible noise, if you want. And the generator is gonna, as usual, use those two concatenated things to generate stuff, and the discriminator is going to say this really, this not. And you've got an extra term that is going to try to maximize the mutual information between C and the image that you generated. So that's a little mathematical, falls into information theory and stuff, and it involves, just know that it involves an encoder network that they name Q that associates an image to its the latent C, but just C, not Z. And there is a divergence term on those terms that is meant to mean that C is meaningful and it's really associated with the data that you're looking at. Might be a little blurry so far, but again, if you are interested in that for a specific project, you can check the paper. This is an illustration of how good it can be in practice. So you see that with an infogan, they managed to isolate the one of the features is going to be well, the rotation, just like I said. So on the bottom, if they can just change the first, say, dimension of the C2. So it's the second dimension corresponds to the rotation. So if they change it, they get their ones are rotating, and their two, their threes are all rotating. So they by saying I only have 10 meaningful dimensions, they managed to disentangle those dimensions so that each one of them corresponds to a salient feature of the data. That's the rough idea behind infogans. Is this clear? Hope so. All right, adversarial autoencoders. They're sort of a combination of VAE and GANs. So actually, they're like they're pretty much a VAE in the sense that you've got an encoder that takes an image, associates a latent representation. A decoder is trying to generate back the original image, and you have a divergence term between the input and the output. The GAN part is for the part of the VAE where you're trying to match the latent representation to a distribution. say a Gaussian. So remember that in the VAE, what you are doing is minimize some sort of maximize some sort of bound on the KL divergence using some math, which leads to not minimizing exactly what you want. In an adversarial autoencoder, what you're going to do is use a discriminator to do this job. So the discriminator is going to, instead of taking images, real and fake images, the discriminator is going to take latent representation and Gaussian samples. And it's going to say, try to say, this was drawn from a real Gaussian, or this was created from an image by the encoder, and is making the distinction between the two. So you're learning to, with a discriminator, to match the latent representation to the prior that you're trying to match. So the advantages and drawbacks of each network are the adversarial autoencoder, it kind of loses this perceptual loss aspect that we mentioned, because there's again, the difference between a real and a fake image is measured by a traditional loss functions like L2. So from that part, it's similar to a VAE, but it is sharper than a VAE because again, you're not trying to maximize to minimize the bound. You're trying to solve the real problem that you're addressing. So it's not as easy to train as a VAE, but easier than a GAN. The reason it's easier than a GAN is that recognizing, for the discriminator, recognizing real and fake images is more difficult than recognizing real Gaussian and fake Gaussian, because the Gaussian is simple and images are complicated. It's simple as that. So it's somewhere in the middle if you want. It might be interesting sometimes. So you can look at what it gives in practice. Yeah, so on the, let's say on the top left, you can see the image drawn, the data points drawn from an adversarial autoencoder. You see that they definitely match a Gaussian. Forget about the colors, just look at the overall distribution of points. In the A image, it's definitely a Gaussian, but in the C image, where the same thing was drawn from a variational autoencoder, kind of looks like a Gaussian, but also it's a bit weirder and not exactly matching the prior. So the AAE is doing exactly what you'd expect it to do, which is the prior is working is closer to what you actually get. The lower level is the same thing, but with a mixture of Gaussians instead of an actual Gaussian. And right. I think there's two more. So the GANs or bidirectional GANs are again addressing the problem of the lack of an encoder in GANs in a pretty smart way. So what's going to happen is that you've got two generators. You're going to have the generator that takes that takes latent representation and try to associate that with images. And you've got an encoder that takes images and associates them with a latent representation. And you can apply the encoder to generated images or to real images, whichever. And the discriminator is going to try to distinguish real from fake, not only looking at the image, but also at the latent representation. So it's going to compare pairs of real images, encoded real images, with fake images. Fake images drawn from a Gaussian and the Gaussian sample. Is it clear? Do I have? Yeah. So maybe it's clearer with the picture. So like you've seen, the features are randomly drawn from the Gaussian. You plug them into the generator, you get a generated image. And meanwhile, you also have real data that you put into the encoder, and you're trying to generate features that match a Gaussian. And the discriminator is taking pairs of either of those processes and trying to say, is this real, is this fake? All right. All right, cycle GANs are maybe the coolest we're going to see, and also the last one. So they are doing something that we can call image-to-image translation. So basically, you've got one GAN that, like, you've got two distributions, X and Y, and they can be whatever you want. They're not like Y are not particularly the labels of X. It's just two, say, distribution of images, and you're going to try to convert one of the distribution to the other. So you got one of the GANs is gonna is conditional GAN that takes X and generates Y from it, and B is a conditional GAN that takes a Y and generates an X from it. And on top of the discriminators that are gonna say this is really drawn from X, or this is fake, and this is really drawn from Y, and this is fake. So you're going to have two. You also have cycle consistency losses, where you're trying to say, if I encode in what direction, in this direction, and I decode back, I should go back where I started. And likewise, if I go from distribution 2 to distribution 1 and backward. Now, what is this used for? Well, this is what it's used for. So you can, for example, pick, have the distribution X that are images of horses, and Y are images of zebras. And you're able to transform zebras into horses and vice versa. So why is this super impressive? It's because you absolutely don't have any aligned pairs of zebras and horses that are in the exact same position. You just have two distributions that are nothing to do with each other, apart from the fact that they have two animals that kind of look alike, minus some color features. So the cycle GAN is able to do translation without any aligned data. So you can use that with zebras and horses. You can use that to do style transfer from realistic, like real photos to Monet-ish pictures, and vice versa. You can transfer from summer to winter. So that goes back to some image translations things we saw in the beginning. Well, that's how you do them. So that's how you use GAN-like architecture for style transfer. You could, on paper, I think, you could do that for actual translation if you want. Like, say you've got a bunch of text that's in English, a bunch of text that's in German, and they are not. You don't have the actual translation of an image of a sentence from English to German. You just have a ton of unsupervised text. You might be able to use a cycle GAN to do unsupervised translation. Saying that out of the blue, I'm sure someone already has done it. I don't know if I don't have the reference of a paper doing that, but definitely exists. Yeah. So again, this is impressive because you don't need a paired data set to do the translation. So no discriminative methods like the one you've seen before GANs would be able to address that problem. But GANs can do it. And yeah, that's the end of the slide. Any questions on anything in the last 5 minutes? Yeah.
So how do you train again? How do you train that? Because I think your loss function is conflict.
You mean the tricks or the because the
I mean,
yeah the
your loss function is conflict between your generative and your discriminative. So we'll train them separately.
oh. Yeah, so you've got a joint loss that affects both. In general, you would train one after the other. Like you've got the same objective that's written there. So instead of the expectation in practice, it would be like a mini batch or just one sample that you use to modelize the expectation. And you get a term, like a scalar, that the discriminator is trying to make it big and the generator is trying to make it small. So let's say every one iteration, you're going to do gradient ascent on that for the discriminator, and the other one, you're going to do gradient descent for the generator. And if you were doing that in PyTorch, you just have to remember that you need to use a different optimizer for the generator and the discriminator to be sure that they are not trained at the same time. But again, if you do just one, you're going to get into a ton of problems, and you may think, yeah, maybe I should train the 5 or 6 times the discriminator for every generator input, or the opposite. And that's the kind of, there it falls into the questions of optimization tricks that we're going to talk about next lecture.
So when you train generator, you fix the weighting of the discriminator?
Yeah, from the generator's perspective, the discriminator is just a loss function. And from the discriminator's perspective, the generator is just an input.